Hey everybody, Ryan Schumacher here with Chapter 13, Summary of Numerical Analysis and Methods. So, a little bit of background about this chapter. It talks a lot about understanding how complex our world actually is. So it said that about 99% of real-world problems in both engineering and science cannot be calculated by analytical methods. So you might have to ask yourself, what is an analytical method? And I get into that in just a moment or two. It also talked about how knowledge learned through primary, secondary, and higher education is usually only good for rare instances. And lastly, it talks about how science and engineering focus more on what is known as numerical methods. So what is the difference between a numerical method and an analytical method? So on the left is what a numerical method is. So it is highly important in problem solving. It is used to design and assess techniques that give approximate but very accurate solutions to complex problems. And we have to make guesses at solutions and then test them to see how good the solution might be. So it involves framing the problem and using a trial and error across a set of possible solutions. On the other hand, we have an analytical method, which is precise, exact solutions. So this is used a lot in logical steps to calculate the exact outcome. These types of problems are easier to solve when possible, and there are cases that do not allow for analytical methods that lead us to using these numerical method types. So one example I have is this comparison example between the two. So the analytical approach here, if you're trying to find the root of a number, so like a solution, you would obviously add 5 to both sides to get the answer of x equals 5. It's precise, it's exact. But on the other hand, if you're doing a numerical solution, you might start with, like I said, a trial and error or a guess and check method. So you would maybe start at x equals 1, and you'd plug that in. You have 1 minus 5, and you would get negative 4. So then maybe you guess 6 on the higher end. So you take 6 minus 5, you get 1, so you get a positive answer. So we understand that the answer has to be between them. So maybe we try 6 plus 1. We take the higher end, we take the lower end, and then we divide it by 2. So the answer has to be between 7 halves and 6. So it's kind of like getting you to get closer and closer to the answer with this numerical method, but it's not the analytical approach that gives you the exact correct answer. So numerical analysis, as we continue, it's very, very vast. It's very expansive. It divides into very deep components that can be quite confusing at our level that we're looking at. But some research shows that the invention of the computer actually has helped with this because of the speed that the computer has. It actually solves these different types of complex problems. It also talks a little bit about interpolation, which in Chapter 5, which we haven't gotten to quite yet, discusses about the action of estimating a value for a function between values that are already determined. So there's just the typical formula that is used in Chapter 5. So how is it used for numerical analysis? I will say that a lot of this was much more abstract than I ever thought. Some of it can be used in computer-aided design here. You have atmospheric modeling, looking at the different temperature ranges throughout the world. You have calculating trajectories. This one is a baseball example, so you can kind of see how in-depth the formulas are, but they have different methods to do that using numerical values. And like I said, they are very extensive, but the one that I found that is used a lot is actually in designing structures. So one example was the stress on a traffic light beam, and in our book there, in figure 13-3, it outlines how to calculate the amount of stress on a specific traffic light. The work itself can be quite difficult, but the goal is to determine how much stress the beam of the traffic light can hold for safety purposes. So they use different types of numerical methods to determine what is actually going on. It gets even more complex if you want to get into what FEM and FDM are. They are the two most common, finite element method and finite difference method. All right, FEM is used in aeronautical, biomedical, mechanical, and electrical engineering, especially when designing situations where there's thermal, fluid, structural, or electromagnetic environments. And FDM is commonly used in solving the heat equation. So the classroom connection that I made, like I said, they're very complex. They're used primarily in high school and college courses. So they can be used in solving differential equations, understanding derivatives, like I said, higher level content. I go back a lot to this bridge design that I've talked a lot about in this course, but there's a software, it's called West Point Design Software, where students get the ability to use a simulator to build a bridge. They gain the understanding of structural design, how different bridges work around the world, and ultimately they're gaining the perspective of how to design what works and what does not work through the simulation. So as the human, we're not necessarily using the methods, but the computer-aided design with the simulator provides that numerical analysis in this case. So here's a visual of what they could use with that design from that exact website. So something a little bit more engaging, but a lot of it comes from the computer designing in this case. So that's a kind of wrap up of of chapter 13 of numerical analysis. It can be very vast, it can be very extensive, but it can be a little difficult to find it in, a elementary, middle school, even high school setting sometimes. But I'm interested to see what others might think about it, or if they have ever used something of numerical analysis. Thanks.